Okay, so if the last focus lesson was about just mixing water with water, you probably saw this coming. We want to know if we can figure out the final temperature if we mix two different things. So really quickly, let me review what we did last time. Last time what we figured out was this. We figured out that we had one substance, we'll call it M1, that's the mass of it, times the delta T, and that's final minus original. So I'm going to put a little 1 there. And that was going to equal the opposite of the other substance times delta T, the final temperature that we don't know, minus its original temperature. So M1 times TF minus TO, temperature original 1, equals the opposite of M2 times TF minus temperature original for the other substance. So this is where we got to last time. So now, what if we want to mix things that aren't the same? Well, it becomes a little bit problematic, but it's still a pretty easy problem to solve, and let me explain why. I'm going to write something down, I'm going to pause it, and I'll be right back. Okay, here's my horrendous sentence. I wrote, different substances are easier or harder to heat up or cool down. That means that it takes different amounts of energy to heat up different substances. For example, if you hold a piece of aluminum in your hand, it's very easy for your body to heat it up. That aluminum gets warm fast. Let's say you have like 10 grams of aluminum in your hand. And now if you have like a little, like a plastic baggie of water in your hand, and you hold it in your hand the same amount of time as you had the aluminum in your hand, it doesn't get anywhere near as warm, because water is a lot harder to heat than aluminum. Okay, so there's this rating of how easy or hard it is to heat or cool a substance. This rating has a name, and we call that rating specific heat. So the specific heat of a substance is a rating of how easy or hard it is to heat up or cool down that substance. So let me just jump to a web page here. How about right here? So this says specific heat capacity table, and it's got substances in the left column and it's got numbers in the right column. And it's a good idea to pay attention to the units here. It says 25 degrees, so this is just a special at that temperature, and it's in joules per gram degree Celsius. So we need to be in Celsius degrees and grams if we want to be, metric about it. So let's find aluminum. 0.9. Okay, so let me jump back here so I don't forget. Aluminum is 0.9, and water was... Is this alphabetical? I have no idea. You guys probably see it already. Oh, H2O, duh. Okay, so H2O, 4.184. Okay, so 4.184. And this was, our units here were joules per gram degree Celsius. Okay, so I'll just write this over here, joules per gram degree Celsius. So let's make a problem and see how easy it is to solve. Let's say we've got a beaker, and we've got 200 milliliters or 200 grams of water. And let's say that it's at a temperature original is, let's say it's 80 degrees. And then let's say we've got a chunk of aluminum. I guess I'll use, no, I shouldn't use that color. Oh, I got gray. So I've got a chunk of aluminum, and we're going to say that this aluminum is 100 grams, and its temperature original is, let's say it's like 20 degrees Celsius, kind of close to room temperature. So what we're going to do then is we're going to take that chunk of aluminum, we're going to throw it in the water, we're going to ignore any heat that's going out into the environment here. We know what's going to happen, we can't stop it, but we're just going to pretend that we're going to get the perfect answer. So how do we solve this? Well, we already know what equation we're going to use. It's going to be this one, but there's going to be a change in that equation because we have to account for the specific heat, because it's so much easier to heat up or cool off the aluminum than it is the water. Let's just compare them really quickly for a second here. Let's do this. Let's go 4.184 divided by 0.9, 4.6. So basically it's 4.6 times harder to heat or cool water than it is to heat or cool aluminum. And that's why we use aluminum to make our car radiators. It really lets that heat out fast. You just blow a fan over it and you can cool your car engine off really, really well. So how do we do this? Specific heat, we use the letter C for it. So all we've got to do is stick a C in this equation. So we usually write it right here between the M and the T. It's going to make mine kind of sloppy, but hey, you guys are used to me being sloppy. So the negative one, that's going to be the one that was hot, right? That's the one losing heat. So that's the water. So I'm going to write this right here. This is going to be 200 because that was my mass. And that's going to be times. And then the C for water was 4.184. And then we don't know the final temperature, but we do know the original temperature of the water, and it was 80. And so put my negative sign in here. And then the aluminum, its mass was 100. And the specific heat for aluminum is, I forgot it already. Oh, there it is. It's 0.9. And we don't know the final temperature, but we do know the original temperature of the aluminum, and it was 20 degrees Celsius. Okay, so this is looking very sloppy. Let me clean this up some. Okay, so here we have this. I wrote all this red stuff down here. So let me do some math here. So 100 times 0.9, that's just 90. So we got 90, and that's going to get multiplied by the TF. So we're going to have 90 TF minus 90. Okay, so 90 times 20. What's that? Is that 1800? Equals. And then over here, we're going to have 200 times 4.184. So we've got negative 836.8. So negative 836.8 TF. And then we've got negative times a negative. So plus. So then we'll go times 80. And we get a big number. So 66,944. Okay, so now I've got to decide. I think I'm going to keep my TF. I want my final TF to be a positive number. So I'm going to do this. I'm going to add 836.8 TF to this side. And I'm going to do the same thing to this side. 836.8 TF. And let me add that really quickly here. 90 plus 836.8 equals 926.8. 926.8 TF. I'll bring down my equal sign here. So if I took my TFs to the left side, then that means I'm going to get rid of this negative 1800. So I'm going to add 1800 on this side. And I'm going to have to do the same thing on this side. So what do I get here? 4, 4, 7, 8, 6. And then the last thing to do is divide both sides by 926.8. That gets rid of it here. So we've got 68744 divided by 926.8. And we get 74.2 degrees Celsius. Okay, so does this answer make sense? Remember, it's 4.5 times harder to heat water than it is to heat aluminum. So number one, we had a lot more water than we had aluminum. so that should probably make the number stay closer to the 80, right? And number 2, the specific heat for water is like 4.5 times bigger than the specific heat for aluminum. So that would also make the number probably be closer to the 80. So this answer right here, I'm thinking, is a good answer. So there is a video on predicting the final temperature when you mix two different amounts of two different substances.